Therefore, let us look at systems with linear phase. So, this is one example where the system has precisely linear phase. Note that the slope has to be negative because we want the group delay to be positive. Group delay has the physical implication of the delay that is imparted to the input. Therefore, group delay has to be positive, therefore, the slope is negative. So, this is what is called linear phase, and the phase response phi of omega has the form minus alpha times omega. There is another kind of system with linear phase, but this is now called as generalized linear phase, and this is denoted by this, and this phi of omega is given by minus alpha omega plus beta, and if beta were 0, generalized linear phase becomes linear phase. Therefore, what we are going to do is we are going to impose linear phase on the system, and then we will ask the question what condition is satisfied when the system has generalized linear phase. Remember, we are talking about systems with real valued impulse response, therefore, the phase has to be odd symmetric, and hence we are talking about such systems for 1/2 of the frequency response, and we are extending it from minus pi to pi by odd symmetry. So, by this we are assuming real valued impulse response. So, we ask the question under what conditions does a system have linear phase. So, this is the question that we ask. So, what we do is we write the frequency response as magnitude times e to the j phase angle, but now the phase angle is not something that is arbitrary, but it is precisely linear phase. So, we are imposing this phase on the frequency response, and we will see what condition has to be satisfied if this is imposed. And we also know that the frequency response is given by sum over all n each of n e to the minus j omega n. For now, I have written the summation as sum over all n rather than writing it in the usual fashion n going from minus infinity to plus infinity. The implication of this we will see as we go along. Now, let us equate the tangent of the angle on both sides, right. So, this will be sine minus alpha omega plus beta by cos minus alpha omega plus beta. So, this is the tangent of the angle on the left hand side. This of course is minus sum over all n each of n, this is sin omega n, and this is sum over all n each of n cos omega n. So, this is the tangent of the angle of the term on the right. Now, we can cross multiply. So, this is sum over all n each of n sin minus alpha omega plus beta cos omega n. Then I can cross multiply this with this and then take this to the other side, right. If I cross multiply this and this, I got this. If I cross multiply this and this, I will get the term on the right hand side. I will take the right hand side to the left hand side, and because of the minus sign here, I will get a plus sign here, and this will be nothing but each of n sin omega n cos minus alpha omega plus beta. This must be 0. Cross multiply and collect all terms to one side. So, this is sum up over all n, each of n. So, this is of the form sin a cos b plus cos a sin b. So, this is sin of a plus b. Therefore, this is sin of minus alpha plus omega times n plus beta must be 0, right. Sin a cos b plus cos a sin b. Oh, so minus, sorry, this is minus alpha plus n times omega. Yeah, now this is okay. Okay. So, if the system is to have linear phase, then this equation must be satisfied, because we start off with linear phase and have arrived at this condition. Now, we need a solution to this equation, and one solution that is immediate, that is true, which the mathematician would state, would be, what is one immediate solution to this? H of n equals 0, right. So, that is the trivial solution. It is mathematically valid, but practically useless. So, now we are looking at non-trivial solution, right. So, H of n equal to 0 satisfies the above. The question is, does a non-trivial solution exist? So, now if you are given this problem and say you have to solve it, rather than somebody else giving this problem to you, this is the problem that you are grappling with. So, you are so passionate about this, day in and day out, you think about this, you want to solve this. If you keep thinking about some problem long and hard, sooner or later solution will emerge, or you will go to sleep, right. But if you are passionate, you will be thinking about this day and night, and suddenly some spark will come and hit you and you will be able to make some headway. So, if you are grappling with this problem, you will try to simplify things so that to get a feel for what the approach might be. Okay. So, the first thing that you are likely to do is, let us assume beta equal to 0. So, which means you would solve this problem for the linear phase case. Then in general, n from the basic definition of the DTFT should go from minus infinity to plus infinity. Now, you are going to restrict yourself to the case n going from 0 to cap n minus 1. So, we are now looking at the FIR filter case. Okay. So, also let each of n equal to 0 for n outside this set, and hence you are finally left with this problem that you are going to solve, n going from 0 to cap n minus 1 sin minus alpha plus n omega equal to 0. So, this is the simplified version of the problem. Now we want to see whether some headway can be made. So, a bunch of terms are adding up to 0, right? Bunch of terms are adding up to 0, which means some cancellations are going to happen. So, the brain wave that hits the person who desperately wants to solve this because he or she is so passionate about finding a solution, what occurred to that person was something along these lines. The person realized that cancellations have to happen. How about pairwise cancellations? So, this is the first kind of foothold into solving this problem. And the person then thought along these lines, okay, maybe pairwise cancellations are possible, and the person decided to choose the first and the last term. So, you put n equal to 0, then h of 0 times sine of minus alpha omega plus each of cap n minus 1 sine minus alpha plus n minus 1 omega. So, can these two terms cancel is the question. You know that sine of minus theta is minus sine theta. Therefore, suppose n minus 1 minus alpha, which is this term, if this were equal to alpha, suppose if this were the case, immediately this would imply that alpha equal to n minus 1 by 2. Therefore, for this particular value of alpha, the argument of the sign, they have opposite signs. So, this is sin theta, this is sine of minus theta. So, if they have to cancel, you also need if h of 0 were the same as h of n minus 1, then these two terms will cancel because the coefficients are the same. The argument to the sign have equal and opposite angles. Therefore, if this is true, then h of 0 sine minus alpha omega plus h of n minus 1 sine minus alpha plus n minus 1 omega equal to 0 under these two conditions, alpha equal to n minus 1 by 2 and h of 0 equals h of n minus 1. So, this is the first real progress you have made in trying to solve this. Now, the next biggest step comes. If this were true, then following the same pattern, the second term and the penultimate term have to cancel. Therefore, you need h of 1 sine minus alpha plus 1 omega plus h of n minus 2 sine minus alpha plus n minus 2 omega must be equal to 0. Again, you try to follow the same logic. Therefore, you want 1 minus alpha to be the same as minus alpha plus n minus 2. Am I getting this right? Okay, so minus alpha plus n minus 2, I should put n equal to 1 and then n minus 2, right. So, minus alpha plus n, so here I have put n minus 2 and here I have put alpha to be 1. I want them to have oh yeah, so this is alpha minus 1, sure enough, yeah. Now, this is the most crucial step. So, what does this imply? This implies alpha equals n minus 1 by 2. So, this is the person must be heaving a huge sigh of relief. Why is that? Because if now alpha were something else, then all this carefully laid plans of mice and men would have gone astray. So, now alpha mercifully turns out to be n minus 1 by 2, and again you need h of 1 to be the same as h of n minus 2. Therefore, if then this again cancels, right. This is satisfied. Okay, now we have really made significant progress. Therefore, in general, if h of n equals h of n minus 1 minus little n and alpha equal to n minus 1 by 2, then n going from 0 to n minus 1, h of n sin minus alpha plus n omega equal to 0 has a non-trivial solution. We will now just illustrate this with a simple example and then conclude this session. Suppose n equals 4. So, the coefficients go from 0, 1, 2, 3, because you need to go from 0 to n minus 1. So, h of 0 must be the same as h of 3, h of 1 must be the same as h of 2. So, this and this cancel, this and this cancel, right. So, now these will get cancelled for alpha equal to n minus 1 by 2. So, this is 3 by 2 or 1.5. Okay. Now, let us look at n equals 5. If you have n equal to 5, this goes from 0, 1, 2, 3, 4. So, h of 0 must be the same as h of 4, h of 1 must be the same as h of 3, h of 2 does not have any pair. So, it can be some arbitrary number, we will see that, we will see. So, this and this cancel, this and this cancel. Now, this is left without a pair, but remember we are looking at h of n sin minus alpha plus n omega. So, this goes from 0 to n minus 1. So, this is really n minus alpha is n minus 1 by 2, right. In this particular case, alpha is 5 minus 1 by 2, which is 2. Notice that this sample corresponds to little n equal to 2, all right. Therefore, you have the case, you have sign of n minus 2 for this particular example. Therefore, the center sample which corresponds to n equal to 2, independent of the value of the second sample, or rather the n equal to 2 sample, this does not need a pair to cancel, because whatever each of 2 is, it is going to get multiplied by sign of 0. Therefore, this does not need a pair to cancel. Therefore, this works for both n equal to odd as well as n equals even. And just one more comment before we wrap up. We have shown that this is true for beta equal to 0. Does this immediately provide a solution for some other value of beta as well? Plus 2 pi is a trivial modification, plus pi, right. So, the above solution is valid for beta equal to pi also. Yeah. So, anything mod 2 pi, we are only looking at values of beta, that is mod 2 pi. Yeah, it is true for k pi, k being both odd and even, but they will all map to beta equal to pi case. So, now we will see whether there are other possibilities. If you put a condition on omega, then you are restricting the frequency response. You do not want to put a restriction on the frequency response, right. That is why you are restricting these values, alpha and beta, the parameters that you have to play with. Now, let us see in the next class whether there are other values of beta that yield solutions.